In this video, we discuss section 3.26 onwards. It is a definition of singular and non-singular matrices. For the definition, we have a square matrix A is said to be singular if determinant of A equal to 0 and a non-singular if determinant of A not equal to 0. So this is the definition. Equal to 0, we call it as singular. Otherwise, determinant A not equal to 0, we have non-singular matrices. Now we have another definition. Inverse of a matrix. Let A be a square matrix of order n. If there exists a square matrix of order n B such that AB is equal to I is equal to BA, then A is said to be invertible and B is called the inverse of A. This inverse of a matrix is also called reciprocal of A. So in order to get an invertible matrix, we need to find out another matrix B with these properties. AB equal to BA is equal to I. Now we have a remark. The inverse of a square matrix is always unique if it exists. The inverse need not be exist always. If it exists, then it is unique. Because we assume A is a square matrix with inverse with two inverses B and B1. Then we know that AB is equal to BA is equal to I and AB1 is equal to B1A is equal to I. Now we can prove this B1 is same as B because B1 is equal to IB1. This I can be replaced by BA into B1, that is equal to B into AB1, that is equal to B times I, that is B itself. So that means if there exist two inverses, then they are equal. That means there is only one inverse for every square matrix A. Next we have section 3.34 elementary transformations. Elementary transformations are defined as follows. We have three elementary transformations are there. The first one is interchange of any two rows. That means we can interchange two rows of a square matrix or any other matrix. So this operation is called interchange of two rows, the elementary row operation. Second, we have multiplication of a row by a non-zero number k. That means you can multiply every element of a row by a number k. You can multiply the column as well. The third operation is addition of k times the elements of a row to the corresponding elements of another row. I think you might have done these operations in your plus 2 classes when you start studying matrices. If we do all these operations on a row, then we can call these operations are elementary row operations. If you are considering columns, then we can say that these operations are elementary column operations. Now we have a remark. In this remark, we will introduce a terminology. In fact, these are notations for these these elementary operations. The interchange of ith row and jth row of the matrix is denoted by Rij. If we are considering the corresponding columns, we will denote that as Cij. The second elementary operation is denoted by k times Ri. If we multiply each element of the ith row of a matrix by a non-zero number k, And the third one is denoted by Ri plus k times Rj. If we add k times the row Rj to the row Ri, then we can define equivalent matrices. If a matrix B is obtained from A by one or more elementary operations, then B is said to be equivalent to A, and it is denoted by, or these equivalent matrices are denoted by the symbol tilde symbol, that is A is equivalent to B. That means we write A tilde sign B. Next we have section 3.35 elementary matrices. So we start this section with a definition of elementary matrices. The matrix obtained from a unit matrix means identity matrix. The matrix obtained from a unit matrix that is I by subjecting it to one of the elementary operations is called an elementary matrix. That means you can perform any one of these elementary operations to identity matrix. Then you will get a new matrix, that is what we called elementary matrix. You can perform any one of these elementary operations. For example, we take identity matrix first. I take 3 by 3 identity matrix, that is 1 0 0 0 1 0 0 0 1. Then if we perform R23 denotes the interchange of second and third row. So there is no change for the first row. If we interchange second and third, we will get this matrix, and this matrix is called an elementary matrix. You can perform C23 interchange of the second column and third column, then you will get the same elementary matrix. Now we can perform another elementary operation, say 5 times R3. That means we multiply every element of R3 with 5. So there is no change for first two rows. Then you will get this matrix. This is also an elementary matrix. Then you can perform another elementary column operation, C1 plus 5C2. This denotes we add 5 times elements of C2 to the corresponding elements of C1. So there is change only for the first column. So we write the second and third column as it is, and we replace first column as 1 5 0. So you can get this matrix 1 0 0 5 1 0 0 0 1. That is, if we change first column by 1 plus 5 times 0, 0 plus 5 times 1, 0 plus 5 times 0. So this is the addition of 5 times the second row to first row. Now we have section 3.37 inverse of a matrix. We know that inverse exists only if determinant of A not equal to 0. Then we can, if in that case we find the inverse of a matrix by elementary operations, and this method is called Gauss-Jordan method. We can write abbreviated as GJ method. The elementary row transformations which reduces a square matrix A to the unit matrix, that means to the identity matrix. When applied these operations to identity matrix or unit matrix, then we will get the inverse of A. That means first we have to find out all the elementary operations which reduces A to the identity matrix, and we will perform the same elementary operations to the identity matrix. Then you will get another matrix, that is what we called A inverse. So I'll explain this with a simple example. If the meaning of the statement is if A is a non-singular matrix, then we know that if A is non-singular, then A inverse exists. It's obvious. Then write A is equal to IA. I take A as a 1, 2, 2, 5. We can verify that the determinant of this A is 1, so it is not equal to 0, hence it is a non-singular matrix. Then only you will get the inverse of this matrix. So I write 1, 2, 2, 5 equal to 1, 0, 0, 1, 1, 2, 2, 5. That is A equal to IA. So first we have to find out the elementary operations that reduce this 1, 2, 2, 5 to identity matrix. So we will perform the same elementary operations on the identity matrix on the right. So you will get a new matrix on the place of 1, 0, 0, 1. That's what we called inverse of A. First we perform the elementary operation R2 plus minus 2 R1. We know that first we have to multiply R1 with minus R2, then add it to R2. Then we will get 1, 2, 0, 1. That is equal to, we need to perform the same elementary operation on the identity matrix on the right. And we will write the matrix A as it is 1, 2, 2, 5. Now we need to perform another elementary operation. Our intention is to make the LHS as identity matrix. So we will change this R1 to R1 plus minus 2 R2. So we can get identity matrix on the left. Then we write the same elementary operation on the identity on the matrix obtained in the second step. So that is 5 minus 2 minus 2 1, and we will write A as it is. Okay, then we can get a new matrix 5 minus 2 minus 2 1. Okay, this matrix is B, then we can get BA is equal to I, and this matrix B is called the inverse of A.